Good morning, all of you. I am Preeti from BSc Chemistry Honors third year. Today we will read uses of organic and inorganic reagents in inorganic analysis. Introduction. Reagents are those compounds which are used in inorganic analysis for the detection and determination of ions and molecules. A large number of organic as well as inorganic reagents have been used for this purpose. The inorganic precipitating reagents generally precipitate the inorganic species as sparingly soluble salts or hydrous oxides. The organic precipitating agents form sparingly soluble products either through coordinate linkage or through ionic linkage between the inorganic species and the organic precipitating reagent. Advantages of using organic reagents are The advantages of using organic reagents are listed below. First advantage is they are more specific than conventional reagents under certain conditions. Because of this property, they can frequently be used to detect a single type of ion in a complex mixture. Second advantage is they can be more sensitive. Classical semi-micro methods of qualitative analysis will usually not detect much less than 100 gammas of a substance under specific test solutions. Organic reagents, on the other hand, are capable of detecting below 10 gamma in certain cases as well as 10 raised to power minus 3 gamma. Third advantage is they can be adopted in quantitative analysis. The organic precipitates are generally insoluble in water at a given pH and can be separated, dried, and weighed. Those reactions giving colored soluble products frequently show a regular change in color intensity with concentration of substance under test and so are adaptable to an accurate comparison with colors representing concentration. This is the basic idea in the branch of colorimetry. The next topic is common properties of organic reagents. Some of the common properties of organic reagents due to which these are used in inorganic analysis are given below. First property is formation of colored precipitate. Organic reagents form direct characteristic color with the ions to be detected for locating endpoints, that is as indicators employed with volumetric titrations. Second property is formation of precipitate due to difference in solubility. This may be made on the basis of a gravimetric method. Third property is extraction in organic solvent at controlled pH. Fourth property is masking reagents. This increases the selectivity of reagents. Fifth property is difference in volatility. Sixth property is oxidation or reduction to other valency state. Next property is wash liquids. The chemical nature of the organic reagent is important in determining the use of above mentioned properties. Next topic is advantages of organic reagents over inorganic reagents. It is due to the following properties that they are better precipitating reagents than inorganic reagents. First advantage is selectivity. In many cases, organic reagents are somewhat specific. For example, cobalt from nickel using alpha nitroso beta naphthol or dimethyl glyoxime, aluminium from iron using copper-ferron, cadmium from copper using quinaldinic acid, and thiourea can be precipitated. In some cases, adjustment of the pH will often cause precipitation of one constituent alone. By changing pH and solvent conditions, one constituent after another can sometimes be quickly precipitated out. Second advantage is ease of drying. Organic reagents produce compounds that have little affinity for water and dried easily at temperature low enough to prevent decomposition. Next advantage is co-precipitation. Lack of ionic character of organic precipitation products greatly reduces co-precipitation in most cases. For example, the co-precipitation of sodium and potassium with magnesium is much less when the latter is precipitated by 8-hydroxyquinoline than when it is precipitated by phosphate or oxalate. Some exceptions in metals do occur. It has been little studied, but in some cases it is as bad as in inorganic precipitants. Reagents are usually insoluble in water, therefore, it's important not to add an excess of reagent. This is difficult because there is no way to tell when sufficient reagent without excess has been added. Any excess that is insoluble would add to the weight of precipitate. Disadvantages of organic reagents. There are unfortunately disadvantages to use organic reagents. First is volatility. This is the first practical disadvantage of organic reagents. Because chelated compounds are non-polar, the forces between individual molecules in the crystal are not very great. Thus, some of the metallic complexes which are precipitated in analytical chemistry are appreciably volatile above 130 to 150 degrees Celsius, and most decompose above this temperature. Therefore, the drying of precipitate should be done below 130 degrees Celsius to avoid decomposition. Second is impurities in reagents. It is very difficult to prepare an organic reagent of the same degree of purity as, say, inorganic compounds. Impurities present in organic reagents may enter into the precipitate during the precipitation and cause undesirable reactions. For example, dimethylglyoxime exists in three forms: alpha, beta, and gamma. Of these, only the alpha form is specific for nickel. While preparing dimethylglyoxime, gamma form is also formed along with the alpha form. If the precipitation is carried out with this impure dimethylglyoxime, then nickel will be precipitated with some other metals because alpha form is specific for nickel, whereas gamma form can precipitate and other metals also. Next is ketoenol isomerism in such compounds as dithiazone will cause errors in colorimetric work unless conditions are carefully selected. Third is low solubility of the reagents in water. This is the greatest disadvantage which organic precipitates have in comparison with inorganic precipitants. Fourth is higher molecular weight. The very high molecular weights of chelate complexes formed with metal ions reduce proportionality, small errors in precipitation and weighing. Next is colored compounds. Chelate compounds are often highly colored, and since they are usually soluble in organic solvent, they lend themselves to colorimetric or photometric methods of analysis. Next is solubility in organic solvents. Because of their covalent nature, most metal complexes with organic reagents are soluble in non-polar solvents. Chloroform being usually the best, such solvents are used to extract the complexes for colorimetric determination, or they may be used simply for separating one element from other. Thus, the complex of copperas with tripositive iron is very soluble in ether and chloroform, which allow one to remove large amount of iron from solutions containing aluminium. In these extractions, the pH must be carefully adjusted to give the desired separation. Next topic is some important organic reagents. Some of the organic reagents which are generally used in identification of ions are discussed below. First is oxime, whose molecular formula is C9H7ON. It is almost a colorless solid, soluble in organic solvents and mineral acids. It gives yellow color which may be due to the formation of quinoid structure. It was introduced by Helm and Berg in 1927 as analytical reagent. A number of metals give coordination complex with this reagent. Examples of such metals are magnesium, zinc, copper, cadmium, lead, aluminium, iron, boron, gallium, thallium, zirconium. The formation of the complex compounds with the bivalent metal ions like Zn2 positive is shown below. The quantitative estimation of the complex is carried out by drying and weighing the hydrated or anhydrous complex or complex is ignited to oxide and then weighed. In volumetric methods, the precipitate is dissolved by filtering with HCl and then resulting solution is titrated against standard potassium bromate bromide solution. In spectrophotometric method, the estimation of metal ion is carried out by measuring the optical density of the complex. The reagent has been found to be suitable for magnesium aluminium. The reagent is a 2% solution of oxime in 2N-acetic acid. Second reagent is dimethyl This reagent was discovered by L. Schnaff and was applied by O. Brunk in 1907 for the determination of nickel in steel. The structure of this reagent is shown. This reagent gives an insoluble red chelate with Ni2 positive ion in ammonical medium. Solution of palladium salts give characteristic yellow precipitate in dilute HCl or sulfuric acid, but nitrate ions interfere. Solution of bismuth salts also give a yellow precipitate in the presence of EDTA at pH 11 to 11.5. For the studies, 1% solution of dimethyl in alcohol is employed. In spectrophotometric method, the insoluble precipitate is extracted into chloroform, which yields yellow coloration and the optical density is measured. Third reagent is alpha nitroso beta naphthol, also called as 1-nitroso 2-naphthol. The structure is shown in figure. It is an orange brown powder having melting point 109 degrees Celsius, soluble in organic solvents but almost insoluble in water. The reagent is usually employed as saturated solution in 50% acetic acid. This reagent is common for the precipitation of many metallic radicals, but it is used especially for the detection of ferric iron, copper and cobalt with palladium and uranyl salts in slightly acid solution. It gives insoluble colored compounds under suitable conditions. Nickel and magnesium, however, are not precipitated by this reagent. Therefore, the reagent in acid solution is used for the separation of nickel from the cobalt. The reagent has also been used for the spectrophotometric determination of cobalt and a few other metal ions. It is also used for spot test of cobalt. Fourth reagent is cupferron. Cupferron exists largely not in the nitroso-hydroxy form but in the tautomeric amine oxide form. The reagent is usually employed as 6% aqueous solution but is most useful in strongly acidic solution. In strongly acidic solution, it precipitates iron, cerium, niobium, tellurium, tungsten, gallium, and tin. Copper precipitates should be filtered immediately after their formation because cupferron is not very stable in acid solution. Furthermore, precipitation should be carried out in cold since the reagent is decomposed into nitrobenzene on heating. The precipitates cannot be weighed after drying but must be ignited to the corresponding oxide and then weighed. Next reagent is aluminon. It is a ammonium salt of porine tricarboxylic acid. Its structure is shown in figure. It is a brownish red powder freely soluble in water. It forms brilliant color lakes with certain metals, especially aluminium, with which it gives a bright red lake. Aluminon is a dye and it is very important reagent for spectrophotometric determination of aluminium. By adjusting pH of the test solution 7.8, it is possible to estimate 0.005 milligram of aluminium even in the presence of calcium. The reagent is prepared by dissolving 0.1 gram of substance in 100 ml of water. Next reagent is rubinic acid, also called dithioxamide. This reagent is the diamide of dithioxalic acid and is an equilibrium with mixture with its tautomeric diimidoform. The acid form combines with nickel, cobalt and copper to give colored water soluble inner complex salts whose composition is shown in figure. The copper, cobalt and nickel compounds are quantitatively precipitated from strongly ammonical solutions in strong mineral acid solutions. Rubinic acid reacts only with certain metals elements of platinum salts. In addition to above, rubinic acid forms colored compounds with silver, mercury, bismuth and iron. Rubinic acid is not only important as spot test reagent but also as a gravimetric and spectrophotometric reagent. Next reagent is rhodamine B. It is a tetraethyl rhodamine and is represented in structure. Solution of antimony salt in strong HCl react with rhodamine B and the aqueous solution of the reagent changes from red to violet or blue and finally divided. Precipitate separates immediately or after standing. Trace amount of antimony may be detected in the presence of large quantities of tin by means of this reagent. Small amounts of iron do not interfere. Mercury, gold, palladium are precipitated while molybdates and tungstates in acid solution give color reaction with rhodamine B similar to those given by antimony salt. The freshly prepared benzene solution of rhodamine B is preferred to the aqueous solution. Next reagent is benzidine. Its structure is shown in figure. It is a basic reagent and is employed in slightly acidic solution as dihydrochloride for the precipitation of sulfates. The resulting precipitates may be titrated against standard alkali. The important drawback of this method is relatively high solubility of the precipitate in water and even more in dilute HCl. It also precipitates anions like phosphates and tungstates and give crystalline precipitates with a number of metallic ions such as silver, copper, cadmium, gold, zinc. With cobalt and tellurium, benzidine yields a blue coloration in alkaline medium, which is an important spot test for the metal ions. Recently, benzidine in dilute acetic acid has also been employed as a spot test reagent for the identification of some platinum metals like osmium, iridium, and platinum. Next reagent is capirone or alpha benzoin. Its structure is shown in figure. It is a white crystalline solid. It is sparingly soluble in water but fairly soluble in alcohol. It also exists in isomeric beta form. Capirone is used as a reagent for the quantitative determination of copper, molybdenum and tungsten. Alcoholic solution of capirone gives a green precipitate with ammonical solution of copper salt. Precipitation of other metals in ammonical medium is prevented in the presence of tartaric acid. The green precipitate is soluble in dilute mineral acids. Copper can be estimated both volumetric and gravimetrical method by this reagent. The green precipitate is an inner complex whose formation is shown in figure. Capirone also precipitates molybdenum and vanadium ions quantitatively but in strongly acid solution. Vanadium gives a yellow precipitate while molybdenum gives a white precipitate. Tungsten and palladium also appear to be quantitatively precipitated with Alpha benzoin oxime. Figure ETL have recommended the use of reagent for the detection of basicity in slightly soluble materials such as alumina and barium carbonate. Magnesium is next reagent. It is also called para-nitrobenzene azoresorcinol. 1 to 0.5% solution in 0.25 normal in NaOH is generally employed. In alkaline solutions, it forms a bright blue lake with magnesium ions. The sensitivity of this test is influenced by the presence of ammonium salts, so their presence must be avoided. Next reagent is alizarin S. It is alizarin sulfonic acid whose structure shown in figure. It is a dye whose sodium salt is soluble in water and is employed as an analytical reagent. Aluminium salt give a red precipitate with the violet solution of alizarin S in ammonia. Complex is an adsorption complex of aluminium with alizarin sulfonic acid. Adsorption system of this type containing metal hydroxide and a dye stuff are called leaks. Zirconium forms a red-violet colored compound with the reagent under the alkaline solution. Boric acid also forms brilliant red color in UV light by alizarin in sulfuric acid. The reagent has been employed as a spectrophotometric reagent for the above metal ions as well as for few others. Furthermore, its applicability as adsorption indicator in titration of FeCN6 for negative and molybdenum for negative has been reported. Next reagent is nitron. It is a yellow solid. It is insoluble in water but dissolves in acetic acid. Its 10% solution in 5% acetic acid is generally used as a reagent. Nitron with nitrate yields a sparingly soluble crystalline nitrate C20H16 and 4HNO3 in solution acidified with acetic or sulfuric acid. Thus, nitron is a gravimetric reagent for nitrate, perchlorate, perrhenate, tetrafluoroborate, and tungstate also form insoluble salts and can be determined in a similar manner. Numerous other anions, including bromide, iodide, chlorate, thiocyanate, nitrite, and chromate, interfere but may be easily be removed by preliminary treatment. The results in the presence of chloride ions are generally high, possible because of its co-precipitation. Next reagent is salicyl dioxide. The structure is shown in figure. It is white crystalline solid. Melting point is 57 degrees Celsius, sparingly soluble in water. 5% solution of salicyl aldoxime in 50% ethyl alcohol is used as a reagent. The reagent decomposes in solution and should not be kept for more than about 3 days. Salicyl dioxide gives a yellow greenish precipitate of the inner complex of copper salicyl dioxide with acetic acid solution of Cu2 positive ion. Some important reagents are shown in the given table. Precipitation of Al3 positive, Ca2 positive and magnesium 2 positive ion by liquid ammonia, oxalic acid and NH4 whole twice HPO4 respectively can be shown in as Al2SO4 whole thrice plus ammonium hydroxide will give aluminium hydroxide and ammonium sulfate, and aluminium hydroxide ignite to give alumina and water. Then calcium chloride plus H2C2O4 will give calcium C2O4 HCl. It is a white crystalline solid. Melting point is 57 degrees Celsius, sparingly soluble in water. 5% solution of salicyl dioxide in 50% ethyl alcohol is used as a reagent. The reagent decomposes in solution and should not be kept for more than about 3 days. Salicyl dioxide gives a yellow greenish precipitate of inner complex of copper salicyl dioxide. with acetic acid solution of Cu2 positive ion. Thank you.